I introduce a nice tensor category. So N1, N1 type 3 factors. And our objects are homomorphisms. So unitary normal homomorphisms. Well, then our home set. Home set is this, the set of intertwiners. So this is the intertwining property. Right. So, and so like you know, everyone else is right. So drawing pictures, so I want to do it today. So when V is an intertwiner between row 1 and row 2, then I use this picture, of course. And when the W happens to be an intertwiner between, say, row 1, row 2, row 2, row 3, then just a product. Product of the two operators correspond to the composition of the two intertwiners. So let's see. WV is expressed by this picture. Of course. 2W row 3. Right. And usually just identity 1. 1 is expressed by no box. Row. Well, this is potato. So, and if sigma is a homomorphism from P to N, then, well, if V is an intertwiner between row 1 and row 2, then at the same time it is an intertwiner between row 1, sigma composed row 1 and sigma composed with row 2. Yes. So the same operator V is also expressed by this picture. So in tensor category, so usually this is, I think this is written as this, like this, in tensor category notation. So when mu is a homomorphism from M to Q, then the situation is a bit different because, so this operator is an intertwiner between row 1 composed with, let's say mu, and row 2 composed with. So sigma V is expressed as, here you have mu, and you have 1, 3, row 2. So this is my convention. And well, in tensor category, this is, this corresponds to, well, yes, this tensor product. So the basic rule is that if you see, okay, there is a straight line on the right-hand side, then you do nothing. But if there is a straight line on the left-hand side, then you say, sorry, this is mu. You apply mu to the operator. That's a basic rule for the computation and my convention. And from right to left correspond to from top to down, top to bottom. Right. So the natural question is the following. So given one row which is homomorphism from M to M. So is there row bar which is from M to N satisfying so this relation. So this will be row bar, row equal row, and also I need another one. Row bar, row equal row bar. So of course here I should specify something. So this usually this means I suppress identity here. So this is an identity of N. So the question means that are there nice intertwiner between identity and row bar, and also here you have identity of N. So are there intertwiner between row and identity satisfying this relation? That's a real question. And in tensor category, if there is such a row bar, then this object is called dual object, and such a object, such a row having the dual object is called rigid something in tensor category.
So can you suppress you put in that in the top? Shouldn't it appear on the right hand side?
This is identity, so you can suppress it.
If you wanted to put it in, how would it go?
Oh, so this is just a composition of row and identity, so it's just a row. So you can suppress it. The same is true, so composition of identity of N and row, so you can suppress it.
So you can put it on the right, if you want to put it on the right hand side, you have a dotted line to the left and a dotted line to the right.
And the answer is so exists such a row bar if and only if the index is finite. This is finite. Or in my notation, so remember this is the square root of the minimal index.
Sorry, I'm confused by what does it mean to loop? What's the significance of looping? What's the action that happens when you loop together?
Say it again.
The first, where they're sort of looped together. I guess I'm trying to understand from your notation where we were allowed to put one of these guys in.
Yeah.
So what does that mean? Again, can you just say again?
So here, okay, in this diagram you have two intertwiners, one here and the other here. Right. Okay, so maybe I should write this way. Okay, so this is an intertwiner between identity and row bar. This is the intertwiner between row bar, row, and identity. So you compose them, and you get identity. That's what this picture really means.
The row bar is defined up to equivalence?
Yeah, in this picture, yes, it's up to equivalence. Well, once there is such a thing, then it is unique up to equivalence. That's a general factor in tensor category. So I'm going to prove it. So, and let's go back to the situations. A and B are just type 3 factors. And the index is finite. So E is a minimal expectation. So I use only minimal conditional expectation. So whenever I write an expectation, that is a minimum. So then there's a basic construction here. E1, and this is just a. Now, so if you start with type 3 factors, finite inclusion, type 3 inclusions, then A1 is also a type 3 factor. The reason is that, well, actually A1 is a Morita equivalent to B. So when B is a type 3 factor, then A1 is a type 3 factor. So every non-zero projections in A1 are mutually equivalent. So choose isometry with 0 in A1. Satisfy that. So it is an isometry. So of course this is 1, and free 0 with a star is a joint projection. Since identity and joint projections are equivalent, so there is such a isometry. Then, by push-down lemma, so the left support of this isometry is, well, by definition, the joint projection. So you can find with 0, you can find something V. So there exists V in A, satisfying this relation. V0 is, and I want to put a normalizing constant here. Is right constant or not? Yes, this is the right constant. Okay. Then this is an isometry because well, let's compute. So since V0 is an isometry, we have this, and then we have this equation. Then we apply the dual conditional expectations, then we get one is we start with. So this way we get an isometry. Now, so we want to construct what's called canonical endomorphism of Roberto Longo. And for that, so remember this fact. So if you cut A1 by the joint projection, then this is the same as B cut by Jones projection. And this is isomorphic to, as an algebra, this is isomorphic to B. So this means that, well, since V0, the left support of V0 is the Jones projection, so we have this. V0. This is B. So this shows that there exists isomorphism from A1 to 1. This is an isomorphism. Such that, okay, Yes? So this is an isomorphism from A1 on to B. Okay. And and if we want to get rid of this projection, then you apply the dual conditional expectation. Then you get this formula. Oh, I didn't specify. Okay, I'm sorry. I didn't say what this D is. So D is a square root of the index. And it's going to be the dimension function of the canonical endomorphism. So if you apply this, then you get. Right. So now define gamma, which is a homomorphism from A into B. So it's by just a restriction of gamma 0. So the restriction of gamma 0 is our definition of gamma, and this is called the canonical endomorphism.
So you're saying you can do without the two modular operators?
Yeah. No. And well, I need something else. Okay. My goal is to show that when the dimension of rho is finite, then it is rigid. It has a dual. Well, in my word, it's in quantum field theory. Look, algebraic quantum field theory. You don't really say it's dual. It's conjugate. So I use the word conjugate. Anyway, so. Starting from this condition, I want to show the existence of the conjugate endomorphism, and I need one more thing. So that's W, so which is just an image of with 0 by gamma 0. So it is an isometry in B. I think this is enough. Right. So lemma. So first of all, so this B. It is an isometry. It is an intertwiner between identity of A and gamma. Second, W. W is an intertwiner between identity of B and gamma restricted to B. So this is treated as a homomorphism from B into itself. And last, we have this relation. With the W, call, yes, gamma with the W equal 1 over D. Okay, let's prove this. But they almost followed from the definition. First important observation is that gamma 0. Okay. Gamma 0 is an intertwiner between identity of A1 and V0 is an intertwiner between identity of A1 and gamma 0. Yeah, it's almost definition. Yeah, you put the B0 here. Yeah. So this is okay. Also, V is obtained by just applying E1 to V0 with a normalizing constant. What's a normalizing constant here? Try it. Yeah, I think D. Right. We have this. And also, we have this relation. Yes. V0 star B is 1 over D. This also follows from this. Oh yeah, I'll explain it. Because, so this is, you can put, since the left support of V0 is a Jones projection, so you can put Jones projection here. Then, remember, the V is defined by these relations. So this is 1 over D times V0. Start with right. So these are easy consequences of definition. So let's prove. Right. Since gamma is just a restriction of gamma 0 to A, so this relation shows that gamma 0 A equals gamma A. Okay, V0 A equals gamma A. So you just apply E1. Then you get V A equals gamma A. Right, so the first claim, first statement is done. And this is an immediate consequence of this one. Right? So from this, we have, say, gamma 0 V0. Yes, gamma 0. X equal to gamma 0 X. Gamma 0 V0. And this is W. This is W, and the image of gamma 0 is exactly B. So this is just a consequence of this fact. And so, okay. Then first this one. Mr. W. So this is V star gamma 0. Right. And yes, now there is a nice formula for gamma 0 by using the expectation. Yeah, here. So this is V0, V0, V0 star. Sorry. This is, yes, conditional expectation. Yes. So since V is in A, so you can put V star here. So this is a scalar, 1 over D. So you get D times the remaining thing is just a Jones projection. So 1 over D. Right. What remains? Okay. But this is, I think, already done. Yes, because this is nothing but 0. So this is yeah, it's already done. So it's 1 over D.
So we have V0 star B is 1 over D.
Yeah, yeah.
Not V star V0.
This take star.
You get V0 star D.
V0 star B. Yes, it's here.
Oh, I've got it written wrong. look at my house.
Right. So this lemma is enough to assure the existence of the dual conjugate object. So theorem. So let n and n be type 3 factors. And the rho is a homomorphism from m, from n into m. And the dimension is finite. Assume the dimension is finite. Then there exists rho bar, which is a homomorphism from m to n. And isometries. Which is an intertwiner between identity and rho bar rho, and another intertwiner, which goes from identity of m to rho bar, satisfying the following relations. One is rho. Yes, this one over t rho, and another one is R rho over this is 1 over 0. So let me express this equation by using a picture. So here, first, okay, you have a rho here. Then first, R rho comes. Okay. So let's normalize it by putting this down. Okay, consider this. So a rho is an intertwiner between from identity to rho bar rho. So you get rho bar rho. Now you compose this with this. Okay, let's normalize it again. Square root of d rho times r rho plus star. So remember, R rho bar goes from identity to rho bar rho. So its star goes from rho bar rho to identity. Rho, something wrong. Oh yes, it's bar. It's bar. So R rho bar star goes from rho bar to identity. Rho bar to identity. Okay, this is right. So this is the identity.
Both are 0.
Where? What's the question?
Both are 0, I asked. 1 by 0, 1 by 0.
Yeah, so I put square root of 0 here to normalize it. And well, we also have this diagram. Rho bar. So I guess here you have 0 rho bar, and here square root of 0 rho star. Yep. Well, now having this lemma, then it's very easy. You just identify right things with right things. So, okay, let's. So in our situation, A then and B is the image of rho. Okay, and what's rho bar? Then we have a canonical endomorphism here, right? Gamma is a canonical endomorphism. So it is a homomorphism from A into B. So let's define gamma bar by the composition of gamma and rho inverse. Since the image of gamma is in the image of n, so this makes sense. So it goes from M to N. Now, yes, by definition, rho bar rho is gamma, right? So we want to.
The rho using the vertical line here.
Sorry, rho bar is gamma. Yeah, that's the right one.
No, in this picture, that vertical line is down here, rho. The picture on the left.
Oh, this is? Yeah, rho, yes. Yes. And we want to have an intertwiner between identity and rho bar here. So just define our rho bar by V. And in a similar way, so what you do is you define our rho by rho inverse W.
So V is independent of rho. Rho then went into the operator V. V just came from the...
Yeah, so yeah, V depends only on the image of rho.
the image.
Image of rho. Okay. Well, if you replace rho by, say, something else, you can compose some automorphism. You can put some automorphism here. Yeah. So if you put an automorphism of n here, then the image doesn't change, right? Then, in this case, this is just a alpha inverse rho bar. So you get the same. So you get the same canonical endomorphism. So, well, you have actually freedom to put the alpha here. Anyway. Okay. Then this relation is nothing but, I guess, this relation is just this one. And the other one is this one. So this is the proof. Right. So I'm going to use the following notation. So the rho is always a minimal expectation from, say, from M to the image of rho. And sometimes instead of using the expectation, well, sometimes it's better to use what's called the standard left inverse. So that is this one. So this is a map from M to N. And this is called the standard left inverse. Actually, in algebraic quantum field theory, so the standard left inverse was used before, you know. Well, it was used to define the statistical dimensions. Actually, it's quite useful. So this satisfies. So now the bimodular property of E take this form now. Is X. So the nice thing about this sector business is we have a very explicit formula for them. Of course, in planar algebra, you also have a very explicit picture for that. So, for example, this is given by rho bar X. So, by definition, the standard left inverse is given by just R rho star rho bar X. Put rho X here. Okay, if you put rho X here, since Okay, R row is the intertwiner between identity and row by row, so you get just X. So it's identity on the image of row. So it should be a conditional expectation. And actually, there is a nice basis. So this is just a single element. This is a basis for EO. And I'll check. So for that, just compute this. So this is just the square plus star row. This is not bar x. Yes, I should. X. Yeah, this is correct. So from here you get a scalar. This is just a 1 over d. So you get d. Let's write. Let me write this d, just d. So then you can get rid of this part. Then you get rho bar x rho. So since our rho bar is an intertwiner between identity and rho bars, this is x times rho bar star rho. Again, this is a scalar. You get x. So this shows that this is just a single element basis for the minimal conditional expectation. Right.
So there's absolutely nothing so far that hasn't worked into infinity, or even one infinity.
Yeah. Yes. Yes. Actually, it works for O2, the Kunz algebra.
Right.
Yeah.
What is this?
Actually, it works for stable simple C-star algebras. If you work on the multiplier, then. Right. So Jeff asked the question yesterday. So yesterday I proved that, so the the composition of two minimal expectations is again minimal. And Jeff asked if there is a nice proof using pictures. So I'll show you the meaning of the equation. So the key point of the equation is the following, right? There is a nice characterization of the minimal conditional expectations. It was this. So this is proportional to the restriction of E, to the relative commutant. So now, this is just a self-intertwiner space. Right, so let X be in the self-intertwiner space of rho. So let's consider this. Then, so remember the definition. So this is, since the basis is just this, so what you get is square rho bar x rho bar. So let me draw a picture. So up to scalar term, this corresponds to, so x is a self-intertwiner of rho. And R rho bar is intertwiner between identity. It goes from identity and rho bar. So here you have identity. So it corresponds to this picture. So on the other hand, So instead of computing this, let me just compute E rho x, phi rho x. Because, so E rho is just a composition of phi rho and rho. And well, this is already a scalar. So you don't really compute the value of E rho. This is already a scalar. So let me compute this instead of computing E rho x. Then this is a rho bar x rho. So this corresponds to, so first this intertwiner comes, rho bar rho. Then you have x. Then, yes. So this equation means, essentially means that the trace is spherical, sphericality of the object. So rho is spherical. So this means that the rho is a, well, in tensor category language, it's spherical. So you can, to produce traces, there are two ways, okay, but they coincide. Right. I should mention one more thing. Well, maybe I don't really need it today. So let me give you an exercise. Okay, 2 exercises. The first one is exactly what Bon mentioned. So show that the rho bar is unique. Up to equivalence. And wow, this is quite a general statement in fusion category. Once such a thing exists, then it should be unique. And second, well, after you show the first, then the second one is easy. So when rho is so I didn't assume that rho is irreducible. So if rho has this irreducible decomposition, so rho bar is given by this natural sign. Yeah. So you have to construct R rho and R rho bar from R rho I and R rho I bar. Yeah. Actually, this part is a kind of disadvantage for sectors because in bimodules, these are obvious. Conjugate bimodule is defined, even not up to equivalence. So this is a disadvantage. Everything is up to equivalence here.
You're going to have to use some sort of a system to actually prove to.
Yeah.
Continuity.
Sorry?
Continuity also you are needing as exercise.
Say it again?
Continuity of rho delta.
Continuity? Oh, I don't understand. So, what I should do?
Masaki, you mentioned that the finiteness of the index is equivalent to existence of conjugate.
Yes.
To prove one direction.
Okay. Yeah, but the other direction is already given by explicit formula of the minimal expectation and the existence of basis. So, start from just okay, I raise it, but just the existence of rho bar and R rho and R rho bar. Then you can define a conditional expectation by the formula I gave. Yeah. And the same computation shows that it is a minimal conditional expectation. Well, for minimality, then you have to do something. But anyway, so that conditional expectation has a basis. So starting from, say, rho bar, R rho and R rho star, you can construct a conditional expectation of finite index type. I gave already the precise formula for that.
If you vary rho, then rho tilde will vary. So continuity of this function.
Oh, continuity of rho bar. So here I said that
X inverse is
rho bar is defined.
This is like generalized inverse, and continuity of generalized inverse is not automatic.
No, it doesn't make sense. It's defined up to equivalence.
But I mean, in the case of index 1, you still have this basis for 1 element.
You need two. You need push down over. Yes. Right. Okay. Yes. One direct consequence of this thing is that probability reciprocity. So once you have this, well, I raised it, but that's the equation. Then we have a probability reciprocity. So from rho sigma, from this space, so there's a canonical map. Okay, let's fix rho bar. Okay, rho bars. Okay, let's assume so. Okay, they have a finite dimension. Then fix rho bar sigma bar, and R rho bar, R sigma bar. Let's fix everything. Then, okay, the following, you can define the following map. Okay, and this is a linear isomorphism. And the same thing is true for the other way. Sigma goes to, no, this is already, this goes to, yes, mu sigma bar. Okay, these are linear isomorphisms because there is an inverse operation. Inverse is just you pull this down. Yeah. So, in fact, we are we're working on not only the just a tensor category, but on sister categories. So, these spaces have norm metric structures. I have to come back to that point later. But possibly I just state this. All right. Okay. So let me show you some easy applications.
And even reversal law is not so definite, no, for generalized inverses.
What?
Reversal law also is not so immediate.
No, rho inverse is very defined.
Yeah.
Yes, very defined.
What happens to reversal law? Bar of rho sigma, is it sigma bar, rho bar?
Oh.
Because reversal law for generalized inverses is not immediate. For inverses it is immediate. That's also I can make it an exercise actually. You can draw a picture. Yes.
Yeah. So first thing is that so from now on everything is a finite dimension. I mean the dimension of every homomorphism is finite. I mean the image of the
homomorphisms have finite index. Okay, let's assume that. So then, well, it's almost trivial, but rho is irreducible. If and only if rho bar contains identity, and if and only if rho bar rho contains identity. So this is just a consequence of Frobenius reciprocity. Because, okay, so rho is irreducible means that this is one-dimensional. Rho. Then by Frobenius reciprocity, you get the identity rho bar, and also dimension identity rho bar rho. So, assume this is an irreducible inclusion. And finite index. Okay. And let the iota be. So starting from factors, then you have a nice homomorphism from n into n. Okay? Just an inclusion map. So this is inclusion map. And we regard this as a homomorphism from n to n. Then iota bar makes sense, and this is nothing but the gamma. The canonical endomorphism considered as a homomorphism from M into N. So now let's consider the Galois group. Galois group of M and N. So by definition, this is a set of automorphisms of M, which leaves every element of N invariant. Okay, this is the Galois group. Then, okay, and the easy observation is that alpha is an automorphism, which is in the Galois group. If and only if, okay. So this honest equation holds, right? Because this is just an inclusion map. So yeah, honest equation holds. So this shows that, but by Frobenius reciprocity, so this is only, this implies that iota bar contains the alpha. So any element in the Galois group is contained in iota bar. On the other hand, if alpha is contained, then Frobenius reciprocity shows that, okay, this sector is the same as iota. So it means that there exists a unitary. Satisfying this relation. So up to this perturbation. So this belongs to the Galois group. So this shows that you can immediately see the Galois group when you know the decomposition of iota bar. Right. Now, using this fact, so yeah. Now I should tell you why the fixed point factor is obvious too. Right. So this is a irreducible and a finite index. Then there exists a finite group. And the action. So the, say, n is a fixed point algebra. Okay. N is a fixed point algebra of G if and only if. Okay, I should write. So this is a one statement. If and only if. So iota bar is decomposed into automorphisms.
Outer action.
It's automatically outer because of the irreducibility. Okay. So, well, in the irreducible case, then any non-trivial element of the Galois group is outer because simply the relative competence is trivial. And yes. For this direction is that, so we've already seen that if n is a point algebra, then iota bar contains the direct sum of alpha g's.
These are the alphas, right?
Yeah, in the end, it will be an alpha. But while you compare the dimension here, so this is index. So this is just a cardinality of G. And the right-hand side, you compute this index, and this is again the cardinality of G. So both sides have the same index. So it means that this is equality. So if the if n is a fixed point algebra, then iota bar is decomposed into alpha z's. So the other way is the following. Okay, I've already seen that. So this means that after inner perturbation, this equality holds. So let's call this alpha I. Okay. Then you have a now Galois group test. Alpha i's. Then again comparing the dimension, then you get that. Say, well, let's call this index set I. Again, you compare the dimension. Then you get an equality.
Presumably this cohomology contributed to H2 vanishing to be
Yeah.
same as.
Yeah.
The formulas don't do that automatically.
So you.
You can, I guess, because you only have things up to equivalence.
No. Well. So in this formalism, you don't need to worry about non-commutative to cohomology because, well, you define this as alpha I. Then, cohomology disappears.
But you get alpha I, alpha G, alpha H equals some endomorphism times alpha G.
Wow. So alpha I, alpha J, iota is iota. So
it's some IJ, but
so this this is, say, ij, alpha ij. Yeah, but here, okay, how to say here. So this perturbation is automatic by this condition. So I should write this way. So this is, say, okay, let me put it this way. This is theta ij. So, okay, if you deal with theta I, then you need two cohomology balancing. But you don't need to worry about it because you choose a very good lifting alpha I by this condition, by using this condition. Then you don't need to worry about this now because the definition of this is alpha I.
Well, that's because that equality is on the nose.
So by the way, so this tells that yeah, I should take care of the depth 2 thing here. So that characterization essentially means that okay, you start from Mn. So you have identity and Mn. So let's draw the principal graph of this subfactor. Now you go to you want to decompose E naught iota bar, then you get alpha g's. And to show that this subfactor is of depth 2, then you have to stop here. Right? So next step is that, okay. So now you apply iota here, then it is iota. So it only comes back. You don't have any new stuff here. So it should be depth 2. So I think, yeah, since Bohm want to, so you asked me to talk about the conservative endomorphism. So, well, I think I'll talk about, say, the easiest possible non-trivial conservative endomorphism without the subfactor. Right. Before doing that, so let me mention this thing. So there is a duality between cross product and fixed point algebra. So this condition, iota bar iota is decomposed in one-dimensional sectors. This condition characterizes that M is a cross product. And it is also easily shown by using this kind of manipulation, but I omit it. Right, so I talk about what's called the Kanbara-Yamagami category. So let's just start with a finite. Then Kanbara and Yamagami consider what's called the fusion category. So I don't really give you the definition, but well, you don't really need to do it. You just think of the category of endomorphism of type C factor. Consider fusion category. With the set of irreducibles. So it has G plus just one more element, X. And the following tensor, following fusion. This is isomorphic to decompose into G. Then once you assume this, then you know that this is a self-dual because this contains identity already, so it's self-dual. So by Frobenius reciprocity, automatically you have this G tensor X equal X and X tensor G. Then Tambara and Yamagami showed that such a category C is classified by two numerical data. Well, no, the first one is just a choice of the square root. Or I should write this way: square root of the cardinality of this. So you have two choices, plus or minus, and symmetric, non-degenerate symmetric category by character. So actually, yeah. So this forces that these are abelian. And so let me reproduce this result here.
You read before then.
Yes, but so I had a look at my old paper which appeared in '93, and I spent only half page to presenting the concrete formula of a conservative endomorphism. So I don't want that no one understood it. I didn't explain anything. I just put a formula for it. So probably I can claim that I already constructed give a realization of such a category, but I don't want to claim that I already classified it in there. So let me reproduce this result by using the sectors and the conservative endomorphisms. So let's assume nice property like, say, this category is a unitary category and so on. Then such a thing, if there exists such a thing, then it should be realized by the category of endomorphisms of type 3 factor. So let's consider M type 3. And let's consider such a thing exists, say rho. This is an endomorphism of M and alpha G action. Well, at the beginning, it should be I should this way. Such that so rho square is decomposed into alpha G's.
Out of M, right?
Sorry?
Out of M.
Yeah.
Out of M.
Out of M. Sorry. Yes. So then by this kind of arguments, then this is actually a point. May assume this condition. If this doesn't hold, then you change the definition of alpha G. You change the drift of alpha G. Okay. So, well, at the beginning, you have to put say, an inner part. But let's call this alpha G. That kind of thing. Then alpha is an honest action. And yes. So from this fusion, okay, since rho is self-dual, self-conjugate. Rho is self-conjugate because, okay, rho square contains the identity, so that means rho is self-conjugate. So this means that the cross product and the fixed point are isomorphic. So these are abelian. These are abelian.
And well, so let's n be the cardinality of G. Then
Rho equal to rho tilde is called trivolution.
what?
Rho cube is rho, it's called trivolution.
I see.
Legel has it.
So now from this fusion rule, so let's compute the dimension. The dimension rho square should be same as the dimension of this direct sum. And this is n. So this means that dimension of rho is square root of n. Right. So now let's choose. Now, okay, this condition means that R rho and R rho bar are proportional. Not necessarily the same, but after phase they are the same. So this is, say, epsilon times R rho bar. But, okay, we have the two relations here. Yes. We have a two relation here. D, not square root of n. So this means that here, so this epsilon must be real. So epsilon is either plus or minus 1. And we have this relation. This is a square root of epsilon. And that ambiguity, so the choice of the square root corresponds to that.
So why are rho and R rho bar equal?
Well, they are different things.
You say that R rho is equals epsilon and R rho bar. Where did that come from?
Oh, well, now rho is rho bar. They are both intertwined between identity and rho square, and they are isometry. So, yeah.
Absolute values.
So let's call R rho S zero. Okay, so it's an intertwiner between identity and rho square. Okay, so it means that you have this. This relation. Then apply alpha g to the both sides. But remember, we have this exact equality. Okay, this is an honest equality, not up to equivalence. So this means that alpha g 0 is in this intertwining space. So let's call this SG. And this is still an isometry because S0 is an isometry, so this is an isometry. So now we chose good basis for the intertwining space. So we have this decomposition by assumption. And we've already chosen good basis. So now we have this honest equality. So rho square x is SG alpha cx. It's these terms. Okay? And so this family of isometry satisfies so-called the Kunz algebra relation. OM relation. Namely, so their images, okay. So their images are orthogonal, and okay, this summation must be 1. So now our idea is that okay, we want to show that alpha g, by definition alpha g, leaves this algebra invariant. The algebra generated by this invariant, but I want to show that rho also leaves this algebra invariant. The algebra generated by these things invariant. Then every categorical information, 6Z symbols, are encoded by the restriction of rho and alpha to the algebra generated by these guys. That's okay. That's my idea. Then you get important information of the category. Well, basically enough information of the category. Then by using the formula, so I'll get a very explicit formula. Then by using the formula, then we redefine alpha z and rho on this generator. Then you get say realization of the category through the Kunz algebra endomorphism. That's the idea. So let me do it quickly. All right. So first of all, so I think it's easy to determine this first, because this is okay. Since this summation is 1, so we have this equation. This is 1. And we have, by definition, SG is alpha GS0. Right. Yeah, we still have this relation. Yeah. We have this relation. I forgot to put it here. Anyway. So yeah. Since we have that, so using this relation, okay. So using this relation, so we get right. So at least for on S0, we have a very nice, easy formula, expressed form.
S0 had nothing to do with G, right?
So since G's are variance, I use the additive notation. It's a neutral element.
But it's out of row.
So this is the definition of SG. So
Right. But S0 is defined to be out of row.
yeah, arrow, yes.
Nothing to do with G.
Yeah, but it corresponds to the neutral element.
Yeah.
Oh, yeah. Yes.
Everywhere row of S0. That's a relation on the SG, not a relation.
Yeah, that's right. Yes. Yeah. Now, next we consider this relation. So, up to equivalence, rho alpha g is the same as rho, but here we need an intertwiner. And since rho and rho alpha g are irreducible, so the intertwiner is actually unitary intertwiner. So it exists with z. Okay, it's a unitary projective representation such that. So add UZ. Okay, this is equal to rho alpha G. So far I use the aspect of the fixed point here. Okay, but here I'm using the aspect of the cross product. And okay, we have this, but let's see. So this implies that this relation, and since alpha G rho is rho, so rho squared, this means that alpha G is in this self-intertwiner space, and this is nothing but just a direct sum of SGST stars. Rho square is decomposed into alpha G's. So. And moreover, so okay, if you put say S0 here, then you see that okay, this is in this intertwiner space. So it means that you can normalize UZ by this relation. So may assume. So this is just a normalization. They are in the same space and they are isometries. So yeah, just make this normalization. And after this normalization, then this is an honest representation. Okay, 2 cocycles disappears. So UG is an honest unitary representation in this space. So it means that there are characters, one-dimensional representation, satisfying this relation. And okay, this is a character. And by normalization, so chi 0 is a 1. Now, we have also this relation. Why? Yes. So you apply alpha k both sides. Then you see this. So alpha k UG is also an intertwiner between rho and rho alpha G. So alpha k UG should be proportional to UG. So this is and this is yes, k plus h star h minus k g h star. So this shows that the normal, okay, there is a constant here, right? But this means that since UG is normalized this way, so you get the constant is chi minus kg. So this should be chi minus kg times UG. So compare, yes. Okay, compare this formula and that. Then now you get right. Minus kg, hg should be chi h minus kg. So this means that if you define h bracket hg by this formula, then this is a bicharacter. Yeah. Now let me compute this. So this is alpha z S0. So by definition, by the definition of UZ, U star. And we already know this. Epsilon UZ. H G SH U star. So this is, no, sorry, here it's nothing. And get this. So we have a very explicit formula for rho SG. And since rho is a homomorphism, so rho should preserve the orthogonality relation. So this orthogonality implies that this character is a non-degenerate. It's easy computation. So I have no time, but some more computations show that actually this bicharacter is symmetric. And we've already have this very explicit formula.
But we don't have rho SG contained in the algebra of the basis.
Already, yes, rho preserves the algebra generated by SGs. Well, UZ, we have an explicit formula of UZ. Okay, UZ is written by SH star. Yeah. So some more computations show that it's symmetric. Then, we get enough ingredient. Now we define. After that, then we can define a Kunz algebra endomorphism by this formula. Then you check that it's really the right thing. I mean, they satisfy Rho. I mean, right fusion out fusion relation. Rho square is decomposed into the algebra. Yeah.
So you get this endomorphism X.
Yeah, object X.
Yeah. And it's left and right dimensions order of the group.
Yeah, categorical dimension is the square root of the group.
So if you was a binomial, so the subfactor index the order of the group.
Yes, the image of rho is just a fixed point out.
Right.
Yeah. So actually, my original intention is that I want to produce a nice endomorphism type 3 factor whose nice self-conjugate endomorphism of a sub type 3 factor whose image is exactly the fixed point out. That was my original intention. Then I came up with this. That's the view. Yeah, next time I think I'll show some. I don't want to really do this kind of messy computation in the lecture, but so next time I'll come back to my original styles. but since Bon asked me to do it, so I spent last 30 minutes for this computation.